Number system. Math starts with numbers. These are the basic foundation blocks of maths. In order to understand and achieve an excellence in maths, we have to understand the basic concepts of number system. Number line is where we represent all the numbers. We can create a number line by simply drawing a straight line, having pointers at both the ends, which represents the unending nature of this line on both the sides. This number line is the home of all the numbers. Some you will learn in this session, while others in higher classes. We mark the points at equal intervals and name them accordingly. Let's start with the numbers which we use in our daily life. 1, 2, 3, 4, 5 and so on, which extends to infinity, and we always get the next number by adding 1 to its previous number. Mind you, this number line has no end to it. Now, if we collect all these numbers together, we can represent it by naming as natural numbers, denoted by n. So, when we say natural numbers, we mean 1, 2, 3, 4, 5 and so on. On the number line, just before 1, we have 0. Now, if we include this number 0 with the natural numbers, what we get is called the whole numbers. So, whole numbers are the numbers which start with 0 and extends on the right side of number line till infinity. What about the left hand side of 0 on the number line? Yes, we have negative numbers. -1, -2, -3, -4, -5 and so on. Keeps extending as long as you want. No end to it. If we include these negative numbers with whole numbers, what we get is known as integers, denoted by z. So, integers extend on both the sides of number line and includes the whole numbers as well as natural numbers, along with all the negative numbers. Let's have a look back at the number line. What about the gaps or empty spaces in between two integers? Between 0 and -1, between 1 and 2, between 2 and 3. Can we have numbers in between these numbers too? Yes, for example, between 0 and 1 we have 1 by 2. Between 0 and -1 we have -1 by 2. Between 1 and 2 we can have 1 by 3, 1 2 by 3 and so on. Between 2 and 3 we can have 2.5. Between 3 and 4 we can have 3.8. Between 4 and 5 we can have 4.3. Considering these numbers, we get the concept of rational numbers. If we give a general name to this rational number as r, then r can be defined as a rational number if it can be written in the form of p by q, where p and q are integers and q is not equal to 0. A number can never be divided by 0. It is an undefined concept in maths. Why? We will cover in some other session. Mind you, we can have an infinite number of rational numbers between any two given rational numbers. Some examples of rational numbers could be -1 by 2, 1 by 2, 1 by 3, which can also be represented as 4 by 3, 2 by 3 can also be represented as 5 by 3, 2.5 which is actually 25 by 10, and if we simplify it, it gets reduced to 5 by 2. 3.8 which can be written in fraction as 38 by 10, can be simplified further as 19 by 5. Even 4.3 can be written as fraction 43 by 10. All the integers are also rational numbers. Let's say 2 can be written as 2 by 1. -5 can be written as -5 by 1. These numbers fulfill the definition of rational number. Means these can be written in the form of p by q, where p and q are integers and q is not equal to 0. Please also understand that 1 by 2, 2 by 4, 5 by 10, 20 by 40, 25 by 50 are all equivalent rational numbers. We only represent 1 by 2 on the number line and not its other equivalent forms. Means, while representing a rational number on the number line, we choose the number in its simplest form, where p and q are co-prime numbers, no common factors except 1. Apart from the numbers we talked so far, there are still some numbers which are left out. Example, root 2, root 3, root 5, pi, root 14 and many more. These numbers will also have some points on the number line, but these are not rational numbers. Then what are these? These are irrational numbers. So if we give a general name to this irrational number as s, then s can be defined as an irrational number if it cannot, mind you, cannot be written in the form of p by q, where p and q are integers and q is not equal to 0. As mentioned earlier, a number can never be divided by 0. It has no solution, just can't happen, undefined. Some examples of irrational numbers could be root 2, root 3, root 5, pi, root 7, root 14, root 15 and so on. Mind you, root 2, root 3, root 5, root 7, root 14 and others are termed as irrational numbers, and they are mutually exclusive from rational numbers. It simply means a number can either be rational or irrational but not both, unlike as in integers and natural numbers where 1, 2, 3 etc. are integers as well as natural numbers. If we take the group of all rational numbers as well as irrational numbers, then we call them together as real numbers. So the real numbers is a group of all the rational as well as irrational numbers. If you look at the number line, you will see that every real number will have a point on the number line. Vice versa, every point on the number line will represent a real number, which could either be rational number or irrational number. This concept about the uniqueness of a point on number line represented by a real number was given by two German mathematicians, Cantor and Dedekind, in the year 1870. We understand the concepts better when they are explained with the help of some relevant examples and models. So let's move on to a better understanding of what we learned so far. Our first example is about analyzing the given statements for true or false, along with the reasons as to how we concluded to our answer. First section of first example states that every whole number is a natural number. Now, if you understood what we learned in the beginning of this session, you know that whole number W starts with 0 and goes on like 1, 2, 3, 4, 5 and so on. Similarly, the natural numbers n starts with 1 and goes on like 2, 3, 4, 5 and so on. We get the next number in both the lists by adding 1 to the given number, and both the sets continue till infinity. Now, if we look at both the sets, we observe that starting 1, we have all the ascending numbers in both the lists, which are 1, 2, 3, 4, 5 and so on till infinity. Looking at the whole number set, we also observe that 0 is left out. 0 is present only in the set of whole numbers but not in the set of natural numbers. Here, 0 is a whole number but not a natural number. It simply means that all the numbers present in the set of whole numbers are not present in the set of natural numbers. Thus, the given statement is false, which means every whole number is not a natural number. Our second section of first example states that every integer is a rational number. Let us take an integer m. We can write m as m by 1 because the value of m remains the same even when written as m by 1. Here m could be considered as p and 1 as q. M can be written in the form of p by q. P and q are integers and q is not equal to 0. Now, isn't this how the rational numbers are defined? Yes, it fits perfectly in the definition of rational number. Therefore, m is a rational number, concluding that the given statement is true. Every integer is a rational number. Our third section of first example states that every rational number is an integer. Let us take a random rational number 4 by 7. Now, if we divide 4 by 7, we get the quotient as 0.5714285714. This is also known as the decimal expansion of the given rational number. Looking at the decimal expression of 4 by 7, we can easily conclude that it is a non-integer. Therefore, the given statement is false. Every rational number is not an integer. Now let's move on to our second example. Find 5 rational numbers between 1 and 2. We have two methods to do this. Let's understand the first method first. Remember, if there are two rational numbers r and s, then another rational number between r and s can be easily calculated by adding both the numbers and dividing the sum by 2. We are going to apply the same principle to find the solution to this problem. We have 1 on the left hand side and 2 on the right hand side. Let's find out the first rational number. So simple. Just add 1 and 2 divided by 2, we get 3 by 2, which is another rational number between 1 and 2. Similarly, we can find our second number between 1 and 3 by 2, which is obviously between 1 and 2 as well. All the numbers we are going to find in this lies in between 1 and 2 only. Let's add 1 and 3 by 2 divided by 2. LCM is 2 and we get 2 plus 3 by 2 whole divided by 2. Solving it further, we get 5 by 2 into 2, which equals to 5 by 4. Similarly, we can find our third number. Let's do 5 by 4 plus 3 by 2 divided by 2, which equals LCM is 4 and we get 5 plus 6 by 4 whole divided by 2. Solving it further, we get 11 by 4 into 2, which equals 11 by 8. Same way, we can find our fourth number. Let's do 3 by 2 plus 2 divided by 2, which equals LCM is 2 and we get 3 plus 4 by 2 whole divided by 2. Solving it further, we get 7 by 2 into 2, which equals 7 by 4. And here we go with our fifth and final number. Let's do 3 by 2 plus 7 by 4 divided by 2, which equals LCM is 4 and we get 6 plus 7 by 4 whole divided by 2. Solving it further, we get 13 by 4 into 2, which equals 13 by 8. So here we have 5 rational numbers between 1 and 2. Since there are infinite rational numbers in between any two given rational numbers, the numbers may vary in different solutions, depending on which numbers we have taken in the group and in which order. Now let's solve the same question with the second method. Number of rational numbers required is 5. Let's find out the value of denominator to be used first, as it is required to solve this question. Add 1 to the total numbers required, which in our case is 5, plus 1 equals 6. Now write 1 and 2 with denominator 6, so the value remains the same. Here we go. Writing 1 equals denominator as 6, we can write 1 in the denominator here as the value remains same. In order to get 6 in the denominator, we have to multiply denominator with 6, gets us 6. But as we want the value of the number to remain same, we multiply the same number, which is 6 in this case, with the numerator as well. 1 into 6, we get 6. Now we have a rational number 6 by 6, which is equivalent to 1. Let's move on with 2 now. Writing 2 equals denominator as 6. We can write 1 in the denominator here as the value remains same. In order to get 6 in the denominator, we have to multiply denominator with 6, gets us 6. But as we want the value of the number to remain same, we multiply the same number, which is 6 in this case, with the numerator as well. 2 into 6, we get 12. Now we have a rational number 12 by 6, which is equivalent to 2. So let us fill the gap between 6 and 12 with denominators as 6. We get 7 by 6, 8 by 6, 9 by 6, 10 by 6 and 11 by 6. We can observe that these rational numbers are different from what we got by using the first method. Doesn't mean either of these solutions is wrong. Rather, both are correct, because we have infinite rational numbers between any two given rational numbers. You can get a different set of rational numbers and I can get different, depending on how we solve and the numbers which we consider in our solution. Now, how do we differentiate or identify whether the given number is rational or irrational? In order to understand this concept along with the relevant examples, join the next session. Thank you for watching and learning. But please do not subscribe this channel if you are not ready to practice solving these questions yourself. You just can't learn maths by watching this or any other video or tutorial. Maths is all about practice, practice and practice. Subscribe the channel, like the video if you are in love with maths. Appreciate the efforts behind delivering this session only and only if you really mean it. I will help you not only find the solution to your maths problems, but will also help you understand the processes, tips and tricks, steps and procedures to derive the solution yourself. In due course of time, although if you keep following and practicing, you will learn how to crack and solve all the mathematical problems in your course. The more you practice, the more you learn. Please leave your queries, if any, in the comments and I will try to cover it in the upcoming sessions. Believe me, studymare, not anymore.